Hello, and thank you for joining this Stanley Gray lecture. If you'd like to ask a question, you can go to slido.com and use the event code Stanley. I'll now hand over to our host, John Polglaze.
Well, good evening, good afternoon, and good morning, wherever you may be. Thank you for all for joining us. Obviously, Mathieu Courdier, who I have the pleasure of introducing for this Stanley Gray lecture, has elicited quite significant global response. Ches from IMarEST, our coordinator, tells me that previously these Stanley Gray lectures have attracted in the order of 150, 170 participants. At last count, Matthew had 552 interested listeners. So I think that's a real testament to the subject that Matthew's going to present to us. So a little bit about Matthew, you might have already read. He's a PhD candidate at the Australian Maritime College. He has a background in marine engineering and naval architecture, and both in civil and military fields. He also has an MBA, so he's quite well-rounded, and I think he's packed a fair bit into his, to this stage, fairly short career, no doubt with a lot more to come. He's worked in the offshore oil and gas industry with a shipping company in that area. He's also worked for a French naval group in submarine and warship propulsion. So he's at the Australian Maritime College now. He's looking at the behaviour of underwater vehicles. And this particular lecture is about how they might behave in the surface environment. And I have some particular recollections of that because I had the great pleasure of serving in Australian Oberon class submarines. They were great boats. But they were basically a submarine that looked like part ship above the water. So it was a bit of a hybridized hull form that probably was not optimized, I think I can say that safely, but not optimized for either being on the surface or below the water. Obviously, the shape of your hull, the properties that then gives you as far as surface or submerged behavior affects your mission profile and what you can do and how you can best do it. So a lot of work going on there. And Matthew's going to tell us about how he's advancing that particular field. So I'll now hand you over to Matthew. Thank you very much, Matthew.
Yep, thank you, John. I'll just share my screen with you all. Okay, I think you can see it now. So thank you, John. Thank you all for being here. So indeed, today I will speak about my research and I try to explain why it is important. Also why it is interesting, and I'll try to make that speech as interesting as I can. And so more specifically, I will speak about the seakeeping behavior of a surfaced underwater vehicle. So as John just said. Okay, I'm also aware that not everyone here is a naval architect or a marine engineer. So I divided my presentation into 4 parts. At the end of the day, I think you will understand a bit better what is seakeeping, what is an underwater vehicle or a UV, I will refer to them as UVs, and maybe even some basis of hydrodynamics. So I'll start my presentation with a few definitions and then jump straight into my research question on the problem I'm trying to address. From there, we'll talk about the significance of this work on why is this important. And at the end, I'll try to show you what I actually do with some first results on some visual images or pictures of what I'm doing. So first of all, what is an underwater vehicle? Well, it can be a lot of things. This one is a military concept ship from Naval Group. And here we can see a sort of cylindrical hull shape. This one would be around 80 meters long. But sometimes we would refer at something like this one. So this one is an exploration device from Trident subs. This is more of a leisure craft that can go really, really deep into the sea. So this one can go down to 11,000 meters deep. Or we can also refer to this one. These are gliders or smaller. We can refer to them as autonomous underwater vehicle. And they are used most of the time for research or industry purposes. Finally, we can also refer to this. This is a manned submersible, and this is probably the UV we all think about when we say submarine. So this is the short fin barracuda from Naval Group again. But before going further, just a quick reminder. This is what our planet looks like. So this is why we use UVs or underwater vehicle as well. Essentially, this is because there is no other way to effectively explore, monitor, understand 2/3 of the world we're in. So there's a lot of water, like 1,400 million cubic kilometers of water on our planet. So that's a lot. And more of humanity depends on the oceans for energy, for food, for transportation. And so the only way to effectively manage this is with machines or tools that can go underwater. From a military perspective, it's also probably the least detectable way that we have to move anything from point A to point B on Earth. And so we can move people, we can also move sensors, for example, around the world. So there is an enormous potential for underwater vehicle use. And basically, we can divide them into 3 main categories. So the first one is commercial or civilian use. And here we can find a research or industrial vehicle, or like this one, other vehicles that are used for tourism. So if you want to rent or to buy a submarine for your holidays, you can go on that website, and there's a few available. The second category is for naval or military use. And here we would sort them into 2 main categories, which are nuclear and conventional, referring to their propulsion power. So one is nuclear and the other one is diesel electric. On that picture here is an Australian submarine that was in Hobart last week, I believe. And we can also refer to mid-jet submarines. So it's tiny submarines used for military applications as well. Finally, the last class of submarine or underwater vehicles, right, would be like the special types. So all those ones we cannot put in the categories A or B. So it's either tools that can go really deep into the sea or rescue submarines. And so my research is not related to all of them, obviously, because we've seen a lot of different shapes, a lot of different purposes here. So actually, I will segregate them a bit differently again. I'm working on something with that shape. So this shape is something engineers like to define by a group of equations, but basically there's a cylindrical mid-body with a conical nose and a conical tail. On top of this, we can add various appendages like the sail that we see here, or rudder blades, appendages at the aft of the UV. They are here to help with stability or steering control, for example. So my point here is that I work on a longitudinal shaped underwater vehicle. We can refer to them as torpedo shaped hulls or bodies. And this is of importance because actually this is a shape that has been optimized for a long time now. So to understand this, let's go back, take a look into the past. This is a typical shape of an underwater vehicle used during the World War I and World War II. There were no major evolution in the hull shape between these 2 wars. And what we can note here is that the UV doesn't fit to the modern definition or to the modern shape I just explained to you. In fact, it's much closer to a surface vessel shape that you've all seen before. So surface vessel have a pointy bow, UVs have a torpedo-shaped bow, so a rounded bow. So this picture here shows a submersible. And despite the fact that it can go and travel underwater, it would spend most of this time at the surface. Hence, the hydrodynamic shape is actually a blend of the surface vessel and the submarine hull shape. Now, during the Cold War, the US have carried out a lot of research to try to develop a modern submarine with much more optimized hull shapes. Because that's how it would become a significant advantage for them during the conflict. So they introduced step by step what we call today the teardrop form, resulting in a lot of hydrodynamic optimization. They also achieved with that form a high propulsive efficiency to maximize submerged performance. That's good, but at the expense of surface performance, because they try to design an underwater vehicle that would be optimized for underwater operations. And it's this same shape or like derivation of that shape that we can see widely used today. So as seen as that picture. So these pictures come from a review of autonomous underwater vehicle. So it's quite comprehensive in terms of shapes we can find. It's also a paper that is available in open access if you're interested. But one thing that is not really clear on that picture is the scale. What are the scales of this underwater vehicle? So regarding AUVs, they can come in kid-sized toy or in adult-sized toys. Another picture, this one is the AUV that we have here at AMC at the Australian Maritime College, and it is used for Antarctic research. So this photo was taken after an expedition beneath the Southern Glacier in East Antarctic in 2019. And so this AUV can dive down to 5,000 meters, so that's already pretty significant. And we see what size that represents here. What is true with AUVs is also true with submarines. On that first picture here, we see a midget submarine, or actually we see 84 midget submarines. So they are 23 meters long and 46 tons while submerged. This submarine here is also 23 meters, but in width. It's actually the Typhoon class submarine, so a Russian submarine that is 170 meters long for 48,000 tons while submerged. And I believe this is the biggest submarine ever built. Okay, so now we've seen a lot of variability in hull sizes and shapes. I will define two hulls that are particular because that's the one I will work on. These are both submarine hulls. They are open source, so that means that we can share them and share the results amongst different research centers around the world. To my knowledge, there is no AUV equivalent for these hulls, so in open access, and that's why we use submarine hulls, even though my research tackles underwater vehicle more generally. The first one on the left is the Suboff. It's a generic nuclear submarine shape that has been developed in 1999 in the US. So it's a pretty old shape that presents some limitations, especially regarding the hydrodynamic behavior. So we can see, for example, that the appendages of the aft of the hull are quite small in a plus shape. And to be honest, these appendages would actually be too small to be able to steer the Suboff effectively. Also, the parallel mid-body is pretty simple, and the sail shape on the top is very, very basic. Then there is another submarine, the BB2, that is currently the best model we can use. It has been designed to represent a modern diesel submarine shape. It has been developed in Australia from 2004 with further improvement in the Netherlands since 2017, so that's much more recent. On here, we can see that the aft control surfaces, the appendages of the aft are in an X shape. We can also see that the sail gained two appendages, horizontal, and there is now a casing above the hull. So these two hull shapes, Suboff and BB2, are the ones with which I will work. Okay, so now we know a bit more about the UVs and the UV I focus on for my research. But now we can wonder why a surfaced underwater vehicle? I mean, I thought submarines were meant to be operated underwater, right? So why surfaced? Well, that's true. They are meant to be operated underwater. However, all UVs need to spend a substantial amount of time at the surface. So at the start or at the end of a mission, for example, in the case of this AUV here, it's simply to go back home or go back to its mothership at the end of a mission. And here we need to ensure that the launch or the recovery of the AUV will be possible even in adverse sea state. AUV can also go back to the surface from time to time during the mission. So for example, to communicate, it can be to send or to receive some data or to reorient itself, for example. And here, its ability to travel safely at the surface gives the limits of the operability of the AUV. In other words, it gives the limits of the mission. Or for military submarine, they need to go back to the surface to get fresh air. We need air, we need oxygen to run diesel engines, for example. These are man-submersible, or this one, so there's people inside. So we want to be sure that the accelerations of the platform will always remain within acceptable human limits. And as we can see on this last picture, a UV at the surface creates or is subject to waves. You can see it here as well. On this video, we start to see the complexity of a near surface or surface stimulation. We see here that the water is traveling along the hull. We can see different wave shapes, different wave regimes. Now, surfacing for UV is an operation that presents inherent risks and challenges. UVs that have been designed to be operated underwater now needs to be in the same environment as the surface ship. So its stability changes, of course, its weight changes, obviously. To be able to surface, the underwater vehicle needs to be lighter than when it is submerged, so that its buoyancy force becomes greater than its weight. Also, its ability to change directions becomes very poor. Its use of sensors becomes also very poor. So on that first picture here, we see the USS Nautilus in 1976 that had a collision while sailing at periscope depth, so just under the surface. On this picture here, we see the USS Hartford in 2009 that hit a cargo ship while sailing the Strait of Hormuz. And the damages don't look as bad as the first picture, but they were over $120 million. That's still pretty significant. And that's not only something that that happened in the past. This picture here is only a few weeks old. It was in February 2021. It's a Soryu-class Japanese submarine that again hit a cargo ship while trying to surface. So this shows some examples of risks associated with surface operation for UVs. We understand now that UV needs to operate at the surface, and that is risky. So this brings us to a problem definition. What needs to be understood? Why am I doing the research I'm doing? So actually, there is an additional level of complexity for UV traveling at the surface compared to a regular ship, because you could tell me like, well, if the submarine is traveling at the surface, then it is in the same environment than a surface ship, and then we already know a lot. It's not completely true. Like we can see here, this submarine is going deep. So it is actually moving in 3D when the surface ship is like stuck on a 2D plane on the surface of the water. So there's an additional level of complexity here. We call it the HIV. It gives the ability to an underwater vehicle to dive. So this 6 degree of freedom is critical for an underwater vehicle, as they operate in a very narrow vertical band. They cannot penetrate beyond the maximum operating depths, otherwise they will be crushed by the pressure. They cannot go too close to the free surface neither, or they will break the free surface. So it has been shown recently that surface UV has some particular behaviors that are not the same as a regular surface ship. It's also not quite the same as their own submerged behavior. So 2 things in particular. The first one, there is a negative added resistance in head wave. So what does that mean? That means that the resistance of the underwater vehicle becomes negative. So for those that are not familiar with the concept of resistance, just think about this. You're in a car on the highway and you put your hand through the window. Now you feel that pressure, the air in your hand, pushing your hand toward. Well, the same thing happened in the water on a hull. Now think about that again. The submarine is experiencing a negative force. So it's like if the water was pulling the submarine forward instead of pushing on it. So it happens in some very particular conditions in head waves. And that's very particular because we've never heard of that for surface ships. The second thing is the motion response of a surface UV. Especially there is a heave and pitch coupling that is different from regular vessels. So this graph here shows the motion response of a ship. Let me show you. The motion response of a ship, function of the wave encounter frequency here. So this wave encounter frequency would increase if the UV travels faster or if the wavelength is shorter. And we can see here in blue the heave and in red the pitch. So heave and pitch both present a peak, as we can see here, and they both are aligned. So this is what we expect usually to see for a surface ship, so the classical heave and pitch motion response for a surface vessel. Now, what we see for a surface UV is this. So here we can see 2 peaks on the pitch, and we can also see that the peaks are not aligned together. Actually, the heave peak is aligned with the pitch trough. So that's very particular. And why is this important? First things first. Well, I told you this is the motion response of a hull function of the weight and cutoff frequency. So obviously we wouldn't want to operate in that area here, in the peak area where the motion would be very intense. So for a surface vessel, there is only one peak region, we know where it is, it's easy to avoid. Now for UV, it's much more complex. So what this is telling us here is that a UV or a surface UV is much more susceptible to adverse motion response to waves. And we call this seakeeping. So a couple of pictures here to illustrate that. The motion of a UV in waves is critical, seakeeping is critical. We can see here that even sometimes submarines need to have a very or incredible even accuracy on control, like on the right picture here, where they are trying to bring in the submarine a human from a helicopter. So here really seakeeping is critical, and this is why my research is important. Now I'll switch to my research a bit more. So who can benefit from what I do, and what do I actually do? To start with, this is the research question I'm trying to answer. So what is the seakeeping response of a surface underwater vehicle in waves? And I think now everyone should understand what is or what means this question. Now it's still a very big question, so I try to answer it in 4 different sub-questions. The first one is, what is the effect of depth on the seakeeping behavior of an UV? Here I try simply to go from deeply submerged condition to closer to the surface to see how it would change the two phenomena I talked to you before. The second one is the effect of wave. So I will simply play with the wave height or wave frequency and see how the two phenomena evolve as well. And the two following questions bring a bit more variability in the research. It's basically to study the influence of hull shape on appendages on the seakeeping behavior of another water vehicle. So really what my work is about is about tackling the operational surface requirement for current and future UV projects. And there are very direct outcomes of this. The first one is the T1000 project. So here in Australia, the Royal Australian Navy is engaged in a big program to design and manufacture 12 submarines that will be regionally superior. And of course, this submarine will be in water for a very long time, and they would benefit from a research like mine. Not only submarines, also AUVs for research, science, explorations. So we know now that AUVs become more and more available for research and science purposes, but not only for research, also for industry, because AUVs can be used to cover a lot of different operations that are in remote or hard to access area or even dangerous locations. And the last point is a bit different. The impact of my work is expected on both the design and the operation of a UV. So in different phases of its life cycle. So submarine design plus manufacture is approximately 15 years. And then they would operate for 30 years. So we can see that my research would have impact over time. There are also two principal novel components in what I'm trying to do. First, I want to give a set of guidance for designers and operators, as I just told you. And I want to do that through a new advanced simulation model. So this is based on 5 new steps in the understanding of fluid mechanics. The first one is the ability to understand and to model the hull and free surface interaction properly. The second one is to understand the calm water resistance of an underwater vehicle in a numerical model. Then we need also to understand the motion response of a fully appended surface underwater vehicle in head waves. And so those steps 2 plus 3 give the next one, which is basically to understand the resistance of a surface UV in waves. And finally, I will investigate the relationship between pressure distribution and phase difference in the heave and pitch phenomenon I explained to you before. Okay, now what I actually do, a few elements of methodology on my work. So I'm working with numerical models. We call them CFD models. So CFD for computational fluid dynamics. But before doing CFD, we need to do some experiments, so experimental fluid dynamics. Basically, experimental fluid dynamics is using yellow submarine models in a pool. So that are physical models that we can touch, we put in a pool, and we do some experiments with them. So we drag them, for example, along the pool, and we record a lot of data, whatever we want to look at. So this is a real world visualization. And when we've done this, we can switch on to numerical models, so computational fluid dynamics. So it's basically using mathematical model to represent what we've seen in the pool before. Now we often hear people saying that CFD is much faster than the experiment or much cheaper. It's not necessarily the case. A good example is, for I spent €1 to develop my CFD model. I would have spent the same year to develop a new experimental technique in a pool, for example. But I think the main difference between CFD and EFD is that experiments give a point measurement of a value, where CFD would show an overall complex flow visualization and can measure all parameters that have been modeled inside. Also, CFD is much more flexible. We can do situations that cannot be constructed in an experiment, for example, or we can do different scales, and it's very easy to swap a scale. We can also test designs numerically even before they are built in real life. So there are really advantages in both experiment and numerical methods, and that's why we work with both at the same time. This is a few pictures of a CFD model. And so the first step in CFD is basically to create a mesh around the hull we're working with. This is a very important step, as the mesh artificially creates a large number of points in the volume we're working on. And then we use all these points to stick on the equations of the fluid mechanics, and then with the computer to solve them. So as for a lot of simulations, meshing is a very important step, and there's a lot of work involved here. As an order of magnitude, the models I'm working with have up to 10 million points approximately. And then we use supercomputers to solve this. It's basically using 120 computing cores and running the simulation for up to 5 days with that. At the end of the process, we can plot a result. So this image, for example, shows a wave on the profile of a BB2 submarine. These are more results of a CFD simulation of a surfaced, fully appended BB2 hull at different speeds. And here we show the surface, the free surface elevation, for different speeds. So what I try to do here, or what I'm interested to do here, is numerically representing something that has been tested experimentally before. And then if the CFD results match what we have seen in the experiments, then we can know, or we can say that we trust the numerical models, and then we can use them to investigate further conditions. So I give you a quick overview on some visual results of what I've been doing last year. So this is a CFD simulation, and I try to compare the CFD picture with the photos from the experiments. So the two photos on the left are from two different runs at the same conditions. So it's two different runs experimentally, but with the same speed on no waves. And so we're trying to see if the CFD matches these photos. So what we can see here is that it matches pretty well, and I'm pretty happy with this. So we can see that the side body wave, for example, has a correct shape and length. We can also see that there is like a wave or a bulb above the nose of the submarine, and there's also a water run-up to the sail of the submarine here. Here we can see a zoom of the previous pictures, clearly showing the water run-up above the hull. And so now I think you can understand that this phenomenon that occurs here on the torpedo-shaped underwater vehicle is not the same as something that would happen on a surface vessel. That's very particular to underwater vehicle. And I spent the last year to try to model this correctly. This is an example of a result graph. Here I plot the drag force, so it gives us an indication of the resistance of the UV. And I compare here two different configurations. So these then help me to inform some choices I need to do for my CFD parameters. So that's the work that I've done. That's in the process of being published, and hopefully you can read it soon. For a visual representation, here's this one, again with the BB2, calm water, surfaced, fully appended. Now the future work, what I will do next. Basically, I'm working on integrating the wave component in the models. So this requires for the UV an ability to move freely in 3 degrees of freedom. So I'm working with an overset mesh so that the CFD can be much more dynamic than what it is now. And that keeps me busy for a few more months for sure. Then on the longer run, or if I look a bit further away, I want to study, so as I told you, different UV hull shapes on appendages. And I also can't help myself but to see similarities in other structures than purely UVs. These are examples of tidal farms for renewable energies, for example. And these are surface body, and they look to me very much like a torpedo-shaped body. And I'm sure it's also very important for them to understand their seakeeping or how they will react to waves. That's future work. I'd like to finish this by acknowledging a few people around me. So first, the DSTG for the support of past student experiments that gave me experimental data to work with. Obviously, also my team of supervisors here at AMC, so Dee Leong, Jonathan Binns, Jonathan Duffy, and also Alexander Conway and Terry Turner. And I also would like to thank the IMarEST for the support toward my project and also for organizing and running this event tonight. Thank you. Now I believe we have some time for questions. So I think it will go to Slido. You can use the hashtag Stanley to connect on Slido and ask the questions.
Okay, thank you very much, Matthew. We're starting to get the questions in through Slido. Some of them quite interesting and probably will quite some searching questions, I think, and I hope we get more to come. So I get to see what comes in, and they also get votes. So I'll go for the most popular and take it from the top. So the first one, Matthew, is can you trim your surfaced underwater vehicle to reduce seasickness on board? Very broad question, I would think.
Sorry, so that's interesting. Yeah, I would say, yes, we can trim a surface underwater vehicle. That's pretty easy to do, especially on the big ones, so like submarines or manned submersible. It's easy to trim. However, I'm not sure if there's a direct link between the trim and the seasickness of people inside. So I'm not sure about this. And actually, I'm not even sure that's something that has been researched before. So I can't answer that question. I'm sorry.
Thank you, Matthew. So the next one, this might actually go to your motivation as well for your particular approach and your thesis that you're doing for your PhD is experimental fluid dynamics versus computational fluid dynamics in terms of costs. Are the two methodologies comparable? And you might want to compare a few other advantages, disadvantages of EFD versus CFD as well, I would think. Thank you.
Yeah, well, it really depends on what we want to do. Doing easy CFD, it's easy. It's quite fast to do. Now, if we try to do something new, like modeling a pre-surface, for example, that's something that is much harder until we need much more time. It goes the same with all the experiments we want to do. If we try to replicate something that we know how to do, it's quite easy. If we want to develop a new methodology to test something new and be very innovative, then it's much longer. In terms of costs, I believe they are quite the same actually. So one of my supervisors worked on other projects before where they had the same cost exactly for experimental and numerical experiments. So it was projects on the America's Cup, so very innovative projects where CFD and EFD were exactly the same budgets.
Okay, thank you for that comprehensive response. Now, the next one refers to your slide 29, but you probably know it off the top of your head. It's, are the CFD computations presented with or without a modelled 3D running propeller? And if not, how might that affect your results?
Yeah, okay. So no, for now, I don't have a running propeller on the models. So that's something we can do. Is there is already CFD done with propellers on ships, for example, even on submerged submarines. That's something we have done before. Not me especially, but that's something that has been done before. I'm not using one here because that includes a lot more complexity in the models. So that would mean that I bring inside the model the ability for the propeller to like rotate by itself. That's not something that I know how to do for now. And also that's not something on which I'm interested for now, because there's already like a lot of questions that have been raised by the hull shape at the surface, and then the appendages shape on influence. And then maybe once we understand better all of these, then maybe we can add a propeller. So that's very interesting work, but I didn't do it yet.
Okay, well, I have a follow-up question to that, actually. You know, in the earlier days of submersibles, most of the submarines were twin screws, and they could be counter-rotating to balance each other out. But now, of course, with the modern teardrop or albacore-shaped hull, most submarines are a single screw. So is there any, what would be the benefit, if any, of perhaps having contra-rotating to reduce torque effects, particularly at speed? Have you ever thought of that?
No, and that's not my specialty here, really. I believe that the most important thing on submarine propulsion is not necessarily the torque or the speed, but it's much more about how discrete, how stealth you can be. Then I think like all the developments that we see now on for the past decades really about submarine propellers or submarine propulsions are all towards having stealthier systems. Then I'm not sure about like how it would impact on the torque or the speed or whatever, but really I think the major developments now are about the stealth on how to have even more quiet submarines. So now we are all like manufacturers are trying to have submarines that are more quiet than the ocean. So that would like make less noise than a bunch of shrimps or fish in the oceans. And I think that's really what drives now the innovation on propellers.
Yes, and not many people talk about actually those aspects of submarine performance for very good reasons. Okay, next questions. How did you account for the effect of free float spaces, such as in the casing and also in the fin or sail in the CFD model?
Okay, well, that's again a very interesting question. That's something that needs to be done, I think, in CFD. However, I'm not doing it for now because what I'm trying to do is a surfaced submarine, so a submarine that is already surfaced. And then there is no more water in the casing. So for those that don't understand that, when a submarine goes from submerged condition to surface, it needs to remove some water out of its hull to get lighter. And so there is some water entrapped in the casing that needs to be removed. So that's not my case here. I'm working on a surface submarine, so the casing is already empty. On all this transitional behavior or area really between the like nearly surfaced and surfaced is something that again we can do maybe later, but there's a lot more questions to answer first.
Thank you. So speaking of questions, this next one is probably the $64,000 question, but in reality, it's probably more like the $640 million plus question. How can you validate the results to full scale? Are the results scalable?
Yeah. How to validate the results to full scale? Well, basically is to try to do something at full scale. So either to take a real AUV or a real submarine and go at sea with it and measure whatever we can measure. It's very hard and very expensive to do. That's why CFD comes handy because on CFD we can model something at real scale. So what I would do is starting with experimental in the pool with a model that is 1.6 meters long. So to look at the physics in the pool on that scale model. Then I would go on the CFD and try to replicate what I've seen in the pool with that same scale of 1.6 meter. And once I'm satisfied with that, and once I think the results are good enough and that I can trust the CFD, then I will scale up this numerical model at the real scale of the real submarine and look at the results there. So yes, some things are scalable, some things are much harder to scale. But again, that's something that research is really working on for now.
Okay, thank you. Now, this next one is probably quite technical, so I'm going to read it out word for word, to make sure that I get it across to you exactly. Okay. Can you explain why you want to use overset for taking into account the waves? There are other alternatives, e.g. deform mesh, to incorporate the sub motions.
Yeah, okay. That's indeed quite technical. I'm not looking in using an overset to model the waves. I'm not sure if I understood correctly the question. I'm looking to use an overset to see how the body will move with waves. So really it's generating waves and then having the body moving through the overset. So I don't know if that answers the question, or that's a pretty technical question. To the author can come to me back by email or a bit later on the chat.
Yes, okay, thank you for that. And that's probably a good idea. Okay, the next one. Have you looked at work done on surface vessels with bulbous bow? So in fact, there's two types of bulbous bow. There's the normal commercial ship bulbous bow, which is essentially an economy measure. And then a lot of warships have a big sonar dome, you know, destroyers and frigates, which is not so prominent on the surface, but nevertheless it's there.
Yeah, so indeed, that's something I've looked at before. There's not a lot of studies on bulbous bow, on the impact on the seakeeping, or at least it's not necessarily related to what I'm doing, because the hull shape of the surface vessel is very different to the hull shape of a submarine or a UV. So yes, I looked at these studies. Some of them are interesting to me, some a bit less. What is interesting though is the swath ship. A swath ship looks like a submarine if you think about it. So there's like a conical part or cylindrical part with a strut on top of it. So that looks like a submarine hull with its sail. And there have been some research on that like a few decades ago that is of big interest to me. But as you all know, there are not a lot of swath ship in operations today, and there's not a lot of research on swath ship neither. So, I mean, I think I'm doing the following of this research.
Okay, that's your second PhD there, maybe. Okay, the next one is what kind of conditions could generate negative resistance on the UV you study? Is this only in calm water or even when added wave resistance is considered?
This is not in calm water. This is only in waves. So the cases we have for now, so what we have tested for now in the towing tank is with head waves only, with some particular wave and counter frequency that I can't tell you everything on top of my head. But again, that's a quite accurate question. So I'm happy to talk about that later or by email. But basically, yeah, head waves.
Okay, thank you. This one's probably a very broad question as well. What parameters have been measured experimentally? How do these compare to the CFD outputs?
Well, yeah, that's true. We measure a lot of things experimentally. We measure some things to understand what we are actually measuring. So for example, in the towing tank, we can ask the towing tank to create some waves, and then we will measure like how high are the waves or how fast are they moving through the pool. That's something that we need to measure. So these are the first type of measurements that helps us to run the experiment. Then the second type of measurements is the one that we want to look at. So for example, we'd measure the drag on an underwater vehicle. And so the drag is something that we can both measure experimentally and then also have numerically in CFD. And that's something I'm really doing every day. I'm looking at the drag of the underwater vehicle. I'm also looking at the speed, for example, so I can know, or we can know easily what is the speed of the vehicle in the towing tank. And then I will try to look at the speed that I'm simulating numerically.
Okay, thank you. Now, this next question reminds me of coming up and surfacing a submarine in the middle of a storm. You move around a fair bit sometimes. But the question is, could you combine near real-time sea surface conditions data with a UUV CFD model to help determine optimal surfacing parameters? And would this be any use?
That's a very interesting question. I think that's something that could be done. I think technically we have what we need to represent numerically like sea surface conditions. Maybe not real time, but something that looks like real time. So maybe like a recording of like the day before, whatever. I think we can do that. I also think we can do UUV, CFD models pretty accurately. Now the question was like, John helped me, was it to determine optimal parameters, surface parameters?
Optimal surfacing parameters. So for a particular set of conditions in operation at your surface, what is the best way to bring your UUV to the surface, to that transition?
Yeah, okay. So, well, to answer the question, yes, I think we can do it. I think that would be pretty interesting, actually. Technically, we can probably do it. I have no idea how to do it, though. That's maybe something in which we can look. Again, future work. I mark that on the side of my head, and yeah, we'll think about it later.
Yeah, I would agree. That's probably a very interesting area of study, considering the explosion we should expect in UUV use across a whole lot of domains in the future. A lot of people are going to be interested in that. Okay, do the CFD results also match the measured resistance of the experiments?
Yes, absolutely. That's the work I've been doing last year. So the first part of my PhD is really to try and develop a CFD model that accurately represents the experiments. And so, yes, I have a research paper being reviewed now that shows the model I've been creating, and that shows that it is validated against experimental results. So, yes.
Okay, thank you. Right, now, what wave spectra did you use? Did you consider, pardon me, fully developed seas as well?
Again, for now, I'm trying to work on calm waters first. And when this work, then I can put some very easy waves, so very regular head waves only. And when this work, then we can try to bring more and more complexity into the models. So fully developed seas, like John swapped wave spectrums or whatever wave we can find. Yes, that's something we can probably do. But again, I'm interested in trying to answer the first questions first, because there's a lot of things we don't understand. There's a lot of things we need to research first. So once the calm model, the calm water model will work, I will jump on head waves model. And then once that works, maybe we can look into more complexities, but that's not my priority yet.
Okay, yes, got to walk before you run, so to speak. Okay, so submarine question here. Operating a submarine at periscope depth in very rough seas is a challenge to keep the boat in trim to prevent broaching. And anybody who's been to see a conventional submarine knows it's also very difficult to keep your ears with not hurting. But so very difficult to keep in trim to prevent broaching. And all degrees of freedom are in action. Do you have any comment on that?
Let me think about that. Yes, so indeed, periscope depths or near surface operations, whatever we call them, are challenging. That's true. Every operation, I believe, close to the seabed, close to a wall, close to another ship is actually very, very complex. So periscope depth, yes, it's challenging. Yes, it's challenging not to break the free surface if we don't want to. Indeed, there is all 6 degrees of freedom involved here. So yes, that's something that we are trying to model here in CFD. That's not something we do in experiments because we cannot really allow 6 degrees of freedom, or that would need that we have a free running model, which is not something we're working with here at AMC. In CFD, yes, that's something we can do. For now, I'm trying to work with 3 degrees of freedom, so surge, heave, and pitch, because the phenomenon I'm trying to investigate are mainly on heave, pitch, and surge. So that's what I'm working with. But again, once we understand that better, yeah, I really want to go up to a 6 degree of freedom model. Yeah, that's really a goal.
It's a lot of computational power required for that, I would think. And that leads into our next question, which is quite a technical question as well, more on the backroom type technicalities. What were some of the main programs used to test and receive data of the 3D computer model?
I'm not sure I understand this question.
What computer programs were you using, basically?
Okay.
For your modeling?
Yeah, okay. So for now, I'm using ANSYS on Fluent especially. So that's one of the 2 or 3 big CFD programs or softwares available. So ANSYS Fluent.
Okay, thank you, Matthew. Next one. In reality, the submarine is propelled with the propeller, however that might look. So are you planning to include the propeller in your calculations?
Yep, okay. So that's something I talked a bit before already about this before. On the long run, yes, it would be great to be able to include the propellers in the simulations we are doing. However, this is very complex. I don't think the propeller influences a lot the phenomena I am working on for now. So yes, that's something we would like to do later. But again, that's definitely not something I will do for now or in the next months.
Okay, unfortunately, we're getting down to running out of time. There's some excellent questions coming in. This one is really good. I like it. Do you plan to consider oblique waves? All naval architects love oblique waves and following seas, etc. Technical requirements often force platforms to operate in unconventional manners, and perhaps not just submarines, naval submarines, but also UUVs that might be collecting data, particularly on long-term data sets and all that. They can't always operate in the way that they would otherwise prefer. So yeah, oblique waves and following.
Yeah, that's a very good remark again. Yes, I would like to include all of these in my work. However, a PhD is only 3 years. My 3 years are already quite full. So that's probably something I would do later. But yeah, I completely agree that tactical requirements or even like everyday operations require something that is much more complex that only calm water or only head waves. So yes, I would like to include this. But again, I would answer again the same way. As long as we don't understand the basics before, it will be very hard to go into more advanced or more complex simulations. Head waves are already quite challenging. But yeah, it would be good to reach that point.
Okay, now I like this question. Did you consider the contribution of dynamic control services, such as forward hydroplanes, to submarine seakeeping in your submarine model? And forward one's particularly useful question, I think, because some submarines do have them mounted up near the bow and others have them mounted on the sail.
Yeah, that's true. On John, your comment on the submarine architecture is very true. However, I am working with the sub-off on the BB2 that are shapes that have been defined before me, and that are shapes that we can work on because we can share them, because we all share the same exact same shape. On BB2, on sub-offs, there are no hydroplanes close to the bow, sorry. So no for that. And for the one on the sail, yes, I could include them. But in the case of a surfaced UV, well, these sail control surfaces are in the air and so are not useful for seakeeping or stability purposes.
Okay, thank you. More of the dilemma of the submarine designer, where to put them and how big to make them. Okay, probably got time for maybe 1 or 2 more questions. Can you see a time when CFD can replace EFD? And if so, when?
It's a very interesting question. The question we try to answer all the time, or we've been asked all the time the same question. To make it simple, no. I don't think it will come. I don't think it will come soon. I'm not sure it will come at all, because CFD is only as good as the validation data we have. And if we cannot validate our CFD with some real world things, real world physics, then we can't use CFD at all. So maybe something that could happen is that we have measurements that are accurate and good enough on real ships, real submarines, real AUVs at sea, that we can post-process smartly enough to be able to use them to validate our CFD. But that's something that would be very, very hard, because what we try to do in EFD is to have a very controlled environment in which we have our UV to operate. The environment is very controlled because we cannot like measure what we're trying to measure in something that is too close to the real world. So that's why we are working in a pool and not in a lake. That's why we are working in a towing tank and not at sea. That's why we are working with simplified models and not with real ship. So maybe that's something that can be done, but not in the near future, I think, unfortunately.
Okay, thank you, Matthew. Now, at the risk of getting in trouble from our coordinator, perhaps going a little bit over time, but I think this last question I'm going to pose to you is a very good one to round out your formal presentation, knowing there's the online forum after this. But what do you see as the outcome of your research? Could it be guidance for designers or guidance for operators of UVs to improve surfaced seakeeping performance? Now, I reckon just about everybody who's been listening to this really stimulating presentation has probably got a whole lot of ideas of where this could go. But I'd love to hear, we'd all love to hear your thoughts on this.
Well, yeah, that's like straight to the point. Actually, what I would like to do at the end of my PhD is really to have a set of guidance for both designers and operators. So designers on what hull shape or what appendages to prefer to try to optimize the surface ability of an UV. And for operators, if, for example, how to orient a hull in waves or what speed to travel to, like depending on what waves we are sailing in. So yeah, I really would like to have a set of guidance for both designers and operators to improve and to optimize the surface shape operation of UVs in general. Yeah, so it would have impact on both the resistance, so that propulsive power, for example, also on the seakeeping performance, to the habitability or the ease of carrying out some missions. So yeah, that's really something I would like to do. Well, we can meet again in 2 years or in a year and a half and see if that's done, or if I need like a few more years to finish that.
Excellent. Okay, well, thank you very much. Now, regrettably, there's still many, many more questions to come, but we just don't have time. You know, great presentation. I particularly remember the bit you mentioned about the plastic bubble that can be used recreationally to go down to 11,000 metres. I'm not sure that's what I would like to call my sort of recreation, but very interesting, very stimulating. As I said, you know, massive participation around the globe. I don't know about Antarctica, but I know that we have people from every permanently inhabited continent have listened in on your presentation. So I think it's great. And I thought it was really interesting, and you're doing really good work. I'm going to hand over to the executive soon, but just to finish off, this webinar is available. It's been recorded, so you can see it again on IMarEST TV. And there's also the Q&A. There's also the online session after this. So I've finished my part. Thank you all very much for attending. Thank you, Matthew, for a really great presentation. Great stuff. It's just going to always generate more questions than this work can ever answer. But it was really good. Good luck with your research. And I will now hand back to Ches at IMarEST. Thank you, everybody.
Thank you, John, and thank you, Matthew, for a fascinating presentation. And thank you to everybody watching. If you would like to continue the discussion, we are holding a private but open networking session. I'll just share my screen so you can see the details. You can head to www.imarest.org/meet now. It will ask you for a password. You can use the password webinar to gain access. And you'll then be able to move around and meet other people who are watching. And I believe that our very own Matthew will be participating in this networking session. So once again, thank you both. And we look forward to seeing you over at the networking session.